This video describes the general concept of frequency response measurement that is relevant to all labs 4, 5, and 6. There is a circuit to be tested. A signal generator is used to generate a test signal, which is a sinusoidal wave of certain frequency and amplitude. The output of the circuit is measured with an oscilloscope. Frequency response is defined as the complex amplitude ratio of the output versus input, which is also described in terms of gain factor and phase shift. To implement the measurement, the input signal is split with a BNC splitter, and one branch becomes the reference input to one channel of the scope. The circuit output is coupled into another channel. Equivalently, and perhaps more conveniently, the Agilent AD can be used to perform both functions, signal generating and scope measurements. Similar to an exercise in Part 0 about using virtual instruments, the quantities of interest are the relative amplitude and phase of the output with respect to the reference input. This is a specific demonstration of the concept, which was also shown in Part Introduction. A square wave is input into the voltage amplifier. The input is represented by the yellow scope trace, the output is represented by the blue scope trace. Although sinusoidal signals should be used for the actual measurement, square wave can give a better insight. At low frequency, the amplifier works as expected. But as the frequency increases, the output amplitude decreases and the wave shape becomes deformed. A purpose of the frequency response measurement is to determine the useful range of frequency of a circuit. For those who are familiar with Fourier analysis, the output roll-off at high frequency can be attributed to the vanishing of the higher-order harmonic components, leaving only the fundamental and few lower-order Fourier components in the output. This is the data of an actual frequency response measurement. The circuit was tested for many frequencies ranging from 0.5 kHz to 800 kHz. The input signal is the yellow trace, which is small compared to the output blue trace at low frequency, as the amplifier had approximately 14 dB gain, or about 27 times. The objective of the measurement is to obtain the ratio of output versus input amplitude, and their relative phase as a function of frequency. These figures are then used to graph a Bode plot or Nyquist plot. In Part Introduction, Step 3, we used an app that simulates virtual instruments. A signal is generated with certain amplitude and phase of the user's choice. On the virtual scope, the signal, yellow, is displayed along with the reference signal in green. The signal amplitude and phase relative to the reference, as chosen by the user, are shown, such as 6.3 dB amplitude gain, and 0.8 pi phase shift in this example. To do frequency response measurement is to do the inverse. Given the signal and the reference, estimate the amplitude and phase. This is easily done, as most digital instruments have built-in functions that can give these estimates with a push of a button. However, one should not automatically assume such a capability, and the AD was found to have a bug in its phase estimate function, which will be discussed further. Meanwhile, learning how to push a button is in itself not essential, and this will be a point of discussion on the learning objective of this part. More practically in this lab course, we will use an app to do the estimate, as shown next. This illustrates the use of an app to estimate the frequency response numerical figures from the data shown previously. The app first asks to select the data folder, then opens all the files of CSV format, which is the recommended format to save data from the AD. If all the data files listed are relevant, select Import All. Wait while the app is importing the files, which may take several seconds, then close all the data import windows. Then click Run. It may take many seconds to minutes to run the calculation, and the outcome are two files. One file shows the Bode plot, which shows the decrease of gain versus frequency, and the phase plot showing a change from pi phase difference to only pi over 2 at higher frequencies. The left-hand side is the conventional 2D Nyquist plot. The 3D Nyquist on the right uses the white arrow axis for frequency, and one can see the large gain with pi phase shift at low frequency, which turns into vanishing gain and pi over 2 at high frequency. A table displays the estimates of various quantities from the data. The second output file is simply a record of calculation output from each data file. There are numerous instruments in the market and most have higher functions such as the app above built in. There is no need for a professional to do such work. What is important for the learning in this course is the understanding of the concepts associated with this type of measurement. An analogy is that anyone can do multiplication with a calculator, and there is no need to do manual work involving large numbers. However, one should understand the principle of multiplication and when to use it. For the frequency response, it is relevant to the knowledge of signal analysis for one to have the basic skills to visually assess the relationship between two signals, what is known as a quick and dirty estimate. Rigorous signal analysis is not required, but the ability to do a quick estimate to see if things make sense is very important in scientific engineering work, what is known as sanity check. Sometimes, one may spend a huge amount of time and effort to conduct some experiment, only to find out later that it has been all wrong because of error, which could have been caught, had some sanity check been done at the beginning. The follow is a story of a fortunate sanity check. This is an app to guide one through exercises to use the AD2. It involves learning to control the signal generators, and the scope cursors to get measurement readings. The exercise involves choosing the scope vertical scale, using the horizontal cursor to estimate a signal peak-to-peak amplitude, then check with the built-in peak-to-peak function. To prepare to do measurement of frequency response of a circuit, the app suggests using the AD2 to generate two signal, one acts as an input reference, and the other simulates the output. The objective is just an exercise how to perform a quick and dirty reading of the amplitude gain and phase relationship of the two signals, to check if they agree with the settings. While doing this innocuous exercise, an alerted student realized something wrong when the student did a sanity check on the phase measurement. This led to the discovery of a bug in this AD2 function. This is an illustration of a step of the exercise. What was found was that when the DC shift slider of a signal generator was moved, there was a small, but consistent phase reading error. Then, at some point, the phase measurement discrepancy became too large to be dismissed as mere statistical error. Visually, the student trusted Ohn's estimate, because it was, after all, it was the sanity check. The video below shows a pitfall when using the phase measurement function of the Agilent AD2 scope. Two identical signals were generated from WaveGen. They have the same frequency and amplitude, are synchronized, and with the relative phase to be zero. The phase measurement function appeared to be correct at first. However, as a DC level offset was introduced to channel 2 signal, the phase measurement gave an incorrect result. As it can be seen in the video, the larger the DC level offset was, the larger the phase error became. This is actually a common algorithm bug, or a better expression is, a common oversight. In processing any sinusoidal signal, it is necessary to separate the signal from its DC offset. In Fourier transform, this is usually a subtraction of the signal by its mean. This mean subtraction approach has potential for small error, but is acceptable if the number of periods in the signals are large. The problem can be solved by modifying the code slightly as shown below. Or better yet, by simply exporting the data to be calculated with an accurate external algorithm. It was just a formula that forgets to subtract the DC level, which may be present in real-life circuit. Fortunately, AD2 allows a user to insert external JavaScript and this error can easily be corrected. However, the problem didn't go away when higher function was used, such as frequency response scan and Bode plot. There is a need for a further modification because this code does not use quadrature. It can determine the absolute value of the phase but not the sign. As it was not known how the AD2 higher function called other subroutines, and the results were erroneous, thanks to Sanity Check, the course decided to use AD2 strictly for direct data measurements. The takeaway of the story is that regardless what algorithm one prefers in signal analysis, it is useful to use the human visual calculation capability to learn some skills in visual signal analysis for Sanity Check. A side note about the app. It calculates directly on the signal and does not use any of AD2 metadata saved in the file, except for the scales and units of time and voltages. Hence, as long as the digital data and the unit scales are correct, it is impervious to other errors. If you are in the lab and use the Keysight scope various built-in functions, errors such as this is unlikely a cause for concern. To switch gear, let's discuss an example where frequency response measurement is essential, the case of Lab Assignment 6. Lab Assignment 6 involves a band-pass filter. It is something that allows AC signals within a certain frequency band pass through, but blocks signals outside that frequency band. When we use Wi-Fi, Bluetooth, or 4G or 5G, we use the band-pass filters for each frequency band of those spectral regions. The top graphs are theoretical, or designed frequency responses. The bottom graphs are experimental results. The agreement between design, top, and measurement, bottom, assure that the circuit was built correctly. This is the same as in the previous, except that the results are graphed with Nyquist Plot instead of Bode. For Lab 4 Part A, measurements involving sinusoidal waveforms will be in the first 4 steps. This last step, Step 5 of Part 1, is simply a preparation for you to be ready for Part A, which is the main experimental work of the assignment. Go through this app, setting up the simulation and practice visual measurements of amplitude and phase with one pair of signals, at a frequency of your choice between 1 kHz and 10 kHz. There is no need for any specific demonstration or precision. Measurement uncertainty within 10% is acceptable. Quick, dirty and crude results are fine. Report the results when you have the ability to perform such visual measurements.